Hello everyone, this is Hassan Shah with my colleague Shoaib Ijaz. We are presenting an FIP presentation under the supervision of our supervisor Dr. Kaim Akhtar and co-supervisor Engineer Manu. So our FIP is topic is the speed control of three-phase induction motor using a GPIC-based motor drive which is controlled. Like if we talk about, we are just controlling the speed of induction motor using different techniques in which we use GPIC board and some FPGA control method. So let's move forward. How this all goes. So let's talk about the three-phase induction motor which we use. Three-phase induction motor is basically a constant speed motor. Like if it is used in variety of applications like homes, industries, everywhere. If we see conveyor belts and all that stuff. So to control the speed and torque of induction motor, there are many old ways in which the power they are not very power efficient. They have number of flaws and there are a lot of power loss. So what we are doing is we are building a method in which we control the voltages and frequency at the same time. So we call this to control the V upon F method. We can control the speed of induction motor. Here we use a PWM technique, which is also called pulse width modulation. In this technique, like we are changing the width of the pulse with respect to time. So it simply means that we are controlling the electricity. PWM technique smartly handles situations like which require many on and off, one or zero, like brightness of LEDs or speed of the motor. Like we do a lot of switching over there in very minimum time. So there for this we use PWM technique. So the two major technique of PWM is the first is the power loss. The power loss is very low in the switching devices and less generated noise. Like the noise is very low, there is no power loss, and ultimately, if we talk about the harmonics and output voltages can be easily controlled with like if we can minimize the harmonics of the output waveform. So this is the two major advantages. So let's move forward to our problem statement. Like we are designing a PWM technique using our GPIC board and the overall decoding circuitry that is we called it like FPGA, field programmable gate array. So and we are analyzing the waveform and apply them to power converters. Like first we give AC and then we convert them into DC, and we do some filters and everything that we'll discuss later in other slides. Here if we can talk about MATLAB, it is like very hard, difficult for the beginners to understand it and complex development methods. And so we didn't use MATLAB in this. We simply used our lab. So in literature, we see that the stator of the induction motor is the point where the power is supplied. Like we give ultimately power to the stator. If we talk about the motor, we know that there are two parts: the rotor inside part and the stator, the outside part. So we are giving power to the stator. So basically, we are looking for the stator voltages to affect the overall control of induction motor. Like to control the induction motor, we are changing the stator voltages for this. And if you talk about, there are three methods to change the speed of induction motor. We can change the poles of the induction motor or variable supply frequency control. Like we can, the frequency is in our hand to change it and to change the speed, or voltage is in our hand with variable supply. So there are many methods where we use a SPWM, which is called the sinusoidal pulse modulation control technique. Yeah, that is also used in many industries that are way more towards a technical word or up to date. They simply do that as we have done here, that we are changing voltages and frequency at the same time to change means to control the speed of induction motor. So we are have simply we are using a technique of SPWM control technique, which is called SPWM control technique, which is very common method and effective method to control the speed of induction motor, like V upon F method as I talked earlier. So this is the circuitry of our GPIC board, general purpose inverter control. So in this, there are two parts. bottom part is of the GPIC and the upper part is the control part that is connected. The whole system is connected with LabVIEW, so in which we have some programs which control the circuitry, so which is called FPGA. So the FPGA board is the upper layer of that board, and the lower layer is that which is called a GPIC SPDOS 9606. So first, what we are doing here, we are controlling the speed of induction motor with V upon F control technique using our that board that I discussed earlier, SPDO 9606 GPIC board. So here we use our PWM technique, pulse modulation technique, that is based on directly on LabVIEW, which regulate the speed of three-phase induction motor. Now our methodology is simple, that we are the upper part that I talked about FPGA based GPIC, the upper part, it's just a control design, like control of the modeling and simulation of all the control design in LabVIEW that we use. And using our board SP0966 GPIC board is directly collaborated with our LabVIEW to control the three-phase induction motor using the ONF method. This is the whole theory. So we will have many circuitries down there in the next slides. We will discuss this. Right? So first we have done that we co-simulate multi-sim with LabVIEW, in which the power circuitry is in the LabVIEW, and we just there is a simply a reference block that is designed in multi-sim, which literally directly relates multi-sim circuitry towards the LabVIEW, which is called co-simulation. It simply needs a drag and drop, which is called the reference block. So the power circuitry is this way. We are giving input, three-phase input to the motor, and we are finding their initial currents, and we are giving some mechanical torque as well, and we have the output like electrical torque and overall the power of the induction motor. And if we say the post simulation first, like if there is a nominal speed of every induction motor, and we have a set point speed, which means that we are changing, we need this amount of RPM to our output, to our induction motor, and there is start time, end time. So we simply giving a three-phase thing, and in short, we say that we have some nominal speed which control the induction motor, and this is the block that is called the reference block, that is co-simulated with LabVIEW, and we have our outputs are voltage and current. Like this is single block, it has many voltages of every phase and all, and we have the output that we are controlling the speed. So what is the waveform of speed, and what is the waveform of electrical torque? So let's move towards the result. If we see that we have a set point of 1450 RPM, like this is our set speed, and the mechanical torque that is we are giving is 2.4. Like after 2.4 seconds, we have the mechanical torque that is 100. And here we see that there are three outputs: one of electrical torque, one of RPM of the motor, and other is the slip. Slip is nothing but the difference between synchronous speed, um, like difference of synchronous speed and inverter speed. Here we see that if we at 2.4 seconds, the electrical torque is a bit higher. Its waveform changes here, and this is the time in which it is showing the red line showing the current of the overall system, and the blue line shows the voltages. And here we see if the speed, if like at start, it has the speed of like after we set our set point is 480. So if we are giving a mechanical torque, after giving torque, the speed gets low because there is something load on the induction motor. And if we see the slip, so as load is included to the motor, so the slip gets higher. This its value gets increased. So there are some changes that we have made. And next we change our set point speed, that is 1800 RPM, and the start time is 4, in which the mechanical torque is 200. So we see that after 4 seconds, the electrical torque is increased. At first, we see the current is so low, and after 4 seconds, the current is increased because If we are giving the torque, mechanical torque, the load is high. The load is high, obviously, then the current will more be consumed in that whole circuitry. So after 4 seconds, we see that electrical torque is increased, and after giving load, the speed is a little bit low after 4 seconds because we give a mechanical torque, and the slip is a little bit increased. Okay. So let's my colleague will start from here. Mr. Shoaib.
Assalamualaikum. From here we have the whole module in which we make a code to control the speed of induction motor. In this we have the some limits to set, that is RPM, maximum speed limits and minimum speed of the induction motor, and that is the maximum modulation index of the induction motor and minimum modulation index. Here is the comparison RPM loop in which we compare if we are that is closed loop and that is open loop. If that is true, that the we are working on the closed loop. If that is false, then we are working on the open loop. Or but in this FYP we are working on the open loop method to control the speed of induction motor. Here is the set point limits that will sets the limits of our maximum RPM and minimum RPM, and that is the output of RPM speed. Here in this technique, view connect method, we cannot control the speed of induction motor through giving input frequency and voltage accordingly, because it is very difficult to, because we have sometimes we have output speed 1200, sometimes 1250, and sometimes 1500, sometimes 1600. There for that we have to control the, we have to calculate the frequency and voltages for according speed, then its frequency and voltage is given to the input. For that reason we have output speed is given at input, that is here. For that speed we will give to the induction motor as the input, then PWM will all adjust the frequency and voltage accordingly to the output speed. Here is the formula, N is equal to 120 F upon P. But in this scenario, we are giving speed as input and we are calculating the frequency as output. So that's why if we can convert or rearrange the formula, then we will say that F is equal to N multiplied by number of poles divided by 120. That is speed F, that is number of poles of induction motor we are using is 4 divided by 120, we are multiplying, and that is the output frequency, that is the frequency of sine and frequency. Then here we create a local variable. Here in this module we are using this frequency of sine and frequency, that we are create a local variable in the previous slide. With this frequency, using this frequency, we are making three sine waves: sine U, sine B, and sine W, that are 120 phase shift apart from each other. And we are comparing that sine waves are using to create the PWM output wave. Here, here in this here in this module, we have comparing, we are making the PWM output signal that will change the frequency and the voltage to control the speed of induction motor. Here we have a triangular wave that is known as a carrier wave, that is the carrier frequency, that is the modulation index, and that is the sine U, sine B, and sine W, that is known as the reference wave. In PWM, we are doing nothing, just we are comparing the carrier wave with the reference wave, and the output is given to the our IGBT switches, that is the PWM. Here we have the when we compare triangular wave with the sine waves, the output of PWM, we have first output we have given to the IGBT switches as same, and the second output is inverted and given to the second IGBT switches. Left side like that, we have given the 6 IGBT switches the inputs, as a PWM, and that is the inverter. If we we put the inverter is a true, then this will forward the signal to the power converter RCP. And if we here we will do the false, then this the signal will never the signal will not forward to the induction motor. Here is the result of V upon F control, where we have make the PWM. That is the carrier frequency is 2000, and the output of RPM is 1000, and the modulation index is 1. At this speed, the frequency and of the induction motor is given is 33.3 something like that. When we increase the speed at 1500 hertz, we can see that the PWM is the voltage also increases of the PWM signal, and the frequency is also increases to 50 hertz. Same like that, we when we increase the speed of the induction motor that is given input in this module, the frequency and voltages adjust accordingly. Here we have see the effect of carrier frequency on the voltage and current waveform. If we set the carrier frequency is 1000, the power quality of the output is very low. There is the harmonics are in the waveform. If we increase the carrier frequency to 2000, then there is some filter out the harmonics. And if we increase the carrier frequency to 5000, that is increase the power quality. But the disadvantage of this carrier frequency increasing too much is that it increase the temperature of IGBT switches, that increase the power losses. That's why we have adjust the carrier frequency is maximum 2000, not in a increase than 2000. Here is we can see the effect of modulation index on the voltage, where we have the modulation index is 1. The output waveforms are smooth. If we sine waves, if we increase the modulation index 1 to 1000.5, the current waveforms are going to non-sinusoidals or square waves towards square wave. That's why we have the modulation index between 0.5 or 1. Here is the conclusion. We have examined that view upon F design method with PWM techniques is most effective way to control the speed of induction motor. If we increase the carrier frequency, the power quality of power quality is also increased. And if we modulation index is direct relation with the voltages, and if we increase the modulation index more, then the waves are going to non-sinusoidal forms. That's why the modulation index values are between 0.5 to 1 to power quality is improved. Here are some references from where we did our literature review.